Hello and welcome back to me answering questions from Robin Hartshorne's Algebraic Geometry. Today I will be answering question 2.7 of section 1. The first part of this question asks us to show that the dimension of projective n space is indeed n. Firstly, the dimension of projective n space is equal to the dimension of the homogeneous coordinate ring of projective n space minus 1. So, S of p to the n is equal to k x naught dot 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 xn over the ideal generated by projective n space, or the ideal generated by homogeneous polynomial functions vanishing on projective n space, which is 0. X naught dot 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 xn over 0, which you're just quotienting out 0, so you're doing nothing. Hence, the dimension of projective n space is equal to n plus 1 minus 1, because this is the polynomial ring over k in n plus 1 variables, so its cruel dimension is n plus 1. So we have shown that the dimension of projective n space is equal to n, and can move on. The second part of this question asks us to show that the dimension of a quasi-affine variety is equal to the dimension of its closure. Firstly, the empty set. The closure of the empty set is equal to the empty set, and we can just ignore it. Let's ignore it. Now, firstly, the dimension of y, assume y is non-empty, because we've just dealt with the empty case. Firstly, the dimension of y is less than or equal to the dimension of its closure, as y is a subsection of its closure. Next, we want to choose ui such that we want to choose an I such that ui subset y is non-empty, which implies that ui subset its closure is non-empty. Now, the dimension of closure is equal to the dimension of ui intersect its closure. Next, phi I from ui to affine n space is a homeomorphism. So, preserves closures. The closure of y intersect ui is this. This is just a property of closures. So, the closure of y intersect ui within phi is this. Now, we then know that the dimension of a quasi-affine variety is equal to the dimension of its closure. Therefore, the dimension of phi of y intersect ui is equal to the dimension of this, which we have shown in question 2.6 is equal to the dimension of y. Wait, phi of this. Terribly sorry, which is equal to the dimension of y intersect ui, which we did this we went through this in the answer to question 2.6, which is thus equal to the dimension of y, which this is one of the results of question 2.6. Now, all we really now need to do is to show that the dimension of this is less than or equal to the dimension of y. So let us do that. Firstly, the dimension of y intersect ui is obviously less than or equal to the dimension of y, as y intersect ui is a subset of y. Now we want to say that we have an equality here. Why do we have an equality here? Well, phi is a homeomorphism, so tilde phi which is the restriction of phi to ui intersect y, is a homeomorphism between y intersect ui and phi of y intersect ui. So closed subsets of 1 are in bijective inclusion preserving correspondence with closed subsets of the other. So, as dimension is defined in terms of chains of descending closed subsets, the dimensions are equal. Hence, the dimension of y intersect ui is equal to the dimension of phi of y intersect ui. Now we have a full chain of things. The dimension of y is less than or equal to the dimension of the closure of y, which is equal to the dimension of phi of y closure intersect ui, which is equal to the dimension of phi of y intersect ui, which is equal to the dimension of y intersect ui, which we have just shown there, which is less than or equal to the dimension of y. Thus, the dimension of y is equal to its closure, the dimension of its closure. And we are done. Thank you for watching. I made a mistake and went and rolled with it, so goodbye.